Welcome to the second lecture of the first chapter of Physics 1 course. In this lecture, we will deal with vector analysis. This is the analysis concerning a certain type of physical quantities. In this lecture, we will discuss the addition of such quantities, which are vectors, and we will discuss this topic, the addition of vectors, using two methods. One is the so-called graphical method. The second is the analytical method. And then we will move to discuss the multiplication of vectors, and under this umbrella we will discuss how do we multiply a vector by a scalar quantity, a non-vector quantity that is. We will discuss the so-called scalar product or the dot product of two vectors. We will finally discuss the vector product or the cross product of two vectors. In physics, there are many quantities. Some of them do not require to be specified fully more than their magnitude and unit. However, many other quantities do require to specify their directions in order to be fully specified. The analysis of these quantities, which require the specification of their direction, needs special tools, special algebra, and it is the purpose of this lecture to discuss these issues. Thus, physical quantities can be divided into two categories. One category is called scalars. A scalar quantity is a quantity that is fully specified by determining its magnitude and direction and unit. The scalar does not need a direction to be specified. The mass and volume and energy and speed are examples of such quantities, scalars. The other category of physical quantities are the vectors. A vector quantity cannot be specified fully and completely without specifying the direction associated with that quantity. The velocity, the force, the displacement of an object are examples of such quantities, the vectors. In order to distinguish between these two quantities, we have to write them differently in a given mathematical equation or in the text even. Thus, we have chosen light blue italic font to represent a vector quantity, and we have chosen an upright yellow symbol to represent a scalar quantity. Now we move to discuss the addition of vectors. How do we add vectors? Vector quantities cannot be added simply like addition of numbers. They require, as we said, special techniques. Graphical method is used to analyze vectors as follows. For example, if we want to add two vectors, vector A and vector B, we choose a point called the origin O, from which we draw vector A. So vector A starts from point O, and we select the right length of that line to represent vector A, the magnitude of vector A. The direction of that arrow represents the direction of the vector quantity A. And from the tip of A, we draw the second vector, which is vector B, with a length that represents the magnitude of vector B and a direction that represents the direction of vector B. The sum of the two vectors A plus B, or the so-called the resultant of the two vectors, is the vector extending from point O to the tip of point B, of vector B. So this dashed line on the figure, this dashed arrow, represents the resultant of A plus B. The subtraction process is exactly the same as the addition process, but we just have to define the negative of a vector. The negative of a vector is a vector that is exactly the same length as the original one, but directed in opposite direction, 180 degrees off. That is the negative of a vector. So this figure shows vector B and vector minus B in green, and when we want to subtract A minus B, this process is equivalent to adding A plus the vector minus B. So that way we convert the subtraction process into an addition process, and we do the process in exactly the same way as we did the addition process before. So A minus B would be the vector, the dashed vector or dotted vector that is extending from point O to the tip of vector minus B, the green vector. This is the subtraction. If we encounter a process where we need to add more than one vector, what do? We follow exactly the same way. We draw vector A from point O with a length that represents its magnitude and a direction that represents the direction of that vector. From its tip, we draw vector B. From the tip of vector B, we draw vector C, and from the tip of vector C, we draw vector D, and finally, the dotted vector extending from point O to the tip of D is the so-called resultant, or the sum of all these four vectors. So R equals A plus B plus C plus D. That way, graphically, we can add four vectors and determine the resultant vector. The length of the resultant represents the magnitude of the sum of the vectors, and the direction of the resultant represents the direction of the resulting vector. The other method which we can adopt for analyzing vectors is the so-called the analytical method. Every vector is specified or can be specified fully by determining components in space. Components in one direction, in another direction, and in a third direction. So every vector consists of components. In order to describe the vector, we have to select unit vectors, vectors of length 1 in specific directions, so that we can use these unit vectors in order to define the directions of the components of the vector that we are analyzing. For example, in Cartesian coordinate system, we choose the coordinates x, y, and z to describe the three components of a three-dimensional vector. And we choose the unit vector I to define the unit in the direction of x, j to define the unit vector in the direction of y, and k to define the unit vector in the direction of z. So that way we have a method for analyzing a vector into three components in the directions x, y, and z. These are, in the figure, the x, y, z coordinates of the Cartesian system, and I, j, k are the unit vectors along these directions. Thus, in component form, a vector can be rewritten as, for example, vector A is written as ax in the direction of x plus ay in the direction of y plus az in the direction of z. So on the screen we see this representation. Ax in yellow represents a scalar quantity, which is the magnitude of the x component of vector A. I in light blue represents the direction, which indicates that Ax is the component in the direction x. And similarly, Ay is the y component in the direction of y, which is represented by j, and Az is the z component, which is in the direction of z, represented by k, the unit vector k. The resultant, or the summation of two vectors using this analytical method, or using component vectors, the resultant is determined as follows. If we have, for example, two vectors to add, a plus b, the resultant is written as vector a in component form with its three components, plus vector b in component form with its three components. In adding, we add similar things together. We never add different things together. So we add the similar components together, and thus we add ax plus bx and the direction of this resultant or this summation is in the x direction. We add ay plus by, and the resultant is in the y direction for this component. And we add az plus bz, and the resultant for this component is in the k direction or in the z direction. And thus, we conclude that the resultant has three components. The x component, Rx, which is equal to ax plus bx, Ry, which is equal to ay plus by, and Rz, which is equal to az plus bz. The vector, as we said, has both magnitude and direction. A three-dimensional vector has three components, and the magnitude of this vector in three-dimensional space is given by the square root of the squares of the sum of the squares of its three components. Thus, the magnitude of a vector A, for example, is equal to the square root of ax square plus ay square plus az square, where ax, ay, and az are the components of that vector. Two-dimension is a special case, and we select this special case for its importance because in many cases any vector can be viewed as a two-dimensional vector if we ignore one of the three directions and consider it trivial, for example. So in this sense, we would analyze a two-dimensional vector as an example. And in this case, vector A has the magnitude of square root of ax square plus ay square. This is the magnitude of a vector in two dimensions, and we assumed that this vector lies in the xy plane. We consider that the z component is 0 for that vector. The direction of that vector can be determined by determining the angle theta which the vector makes with the x direction, for example. This is just a way of determining the direction of that vector. So in that sense, the ratio ax divided by a, which is the ratio of the x component of the vector to the magnitude of the vector itself, is the cosine of the angle theta. The ratio ay divided by y is the sine of the angle theta. And the angle theta is determined by the ratio of the y component to the x component of the vector. So in that sense, we can determine, if we know the components of a vector, we can determine the angle that it makes with the x-axis, and we can determine its magnitude. Now we move to the second topic of this lecture, which is the multiplication of a vector by another quantity. First, we consider the multiplication of a vector by a scalar. So if the quantity s is a scalar quantity and we multiply it by a vector a, then the resultant is a vector which is directed in the same direction of a and has a magnitude that is s times the original vector, the magnitude of the original vector. Dividing a vector by a scalar follows exactly the same steps as the multiplication, since a scalar quantity 1 over s, for example, is another scalar quantity. So we can consider dividing a vector A by a scalar quantity s as being the multiplication of the vector A by another quantity which is 1 over s. And the multiplication is exactly similar to the multiplication. The division of a vector is exactly equivalent to the multiplication. Now we move to another topic, which is multiplying two vectors, two quantities which are vector quantities. And in this case, we have two cases. One case in which we multiply a vector by a vector and the resultant is a scalar, and this process is called the scalar product or the dot product, multiplying a vector by a vector, in which case the resultant is a scalar. And this process is symbolized as vector A dot vector B. The resultant is a scalar, as we said. The magnitude of this resultant is A, magnitude of A, times the magnitude of B times the cosine of the angle phi between the two vectors. So this gives us the magnitude of the dot product of vectors A and B. If we apply this definition of the dot product to multiplying unit vectors with each other, we conclude that the dot product of any unit vector with itself is equal to 1, because the magnitude of each unit vector is 1, and the angle between the unit vector and itself is 0, which gives cosine 0 is equal to 1. Thus, the dot product of any unit vector with itself is 1. And the dot product of any unit vector with any other unit vector is 0, because the angle between any two different unit vectors is 90 degrees, and cosine 90 is 0. If we use vector product, if we use components in scalar product, if we use the component representation, then we write the vector A in its component form, AXI plus AYJ plus AZK, dot B in its component form, BXI plus BYJ plus BZK, and using the definition of the dot product of two unit vectors that is just mentioned a little while ago, we conclude that this dot product in the component form is equal to AX BX plus AY BY plus AZ BZ, which is a scalar quantity. This result is straightforward because, as we mentioned, the dot product of any unit vector with itself is 1, and the dot product of any unit vector with any other unit vector is 0. And this leaves us with the multiplication of the similar components only of the two vectors, as we see. The angle phi between two vectors can thus be determined from the two different definitions of the dot product. Thus, if we write the dot product between two vectors A and B in its two forms, namely A dot B equals A times B times cosine the angle between them phi, and we write it in the second form, a dot b is equal to ax bx plus ay by plus az bz. If we equate these two quantities, we can determine the angle between these two vectors. The second process by which we can multiply two vector quantities is the so-called the cross product. The cross product is the multiplication of two vectors which leads to a vector quantity. Thus, if we call A cross B, if we call it another vector C, C is a vector which has magnitude and direction, and A cross B is the cross product of the two vectors. The magnitude of this cross product is C equals A magnitude times B magnitude times sine the angle phi between the two vectors. Thus, we can calculate the magnitude of the cross product of two vectors if we know the two vectors and the angle between them. The direction of vector C, as we said, it should be a vector. The direction of that vector, which is A cross B, is perpendicular to the plane in which the two vectors A and B lie. And this direction is determined by the right-hand rule. So this rule, which determines the direction of the cross product, if we assume that this is vector A and this is vector B, then vector C, which is A cross B, is perpendicular to this plane which is made by A and B. But since the perpendicular to the plane has always two directions, each plane has two perpendiculars, one up and one down, which one to determine which one would be the direction of A cross B? As we said, according to the right-hand rule, the direction of A cross B is, if we assume that this is A, this is B, then this is the direction of A cross B. Or there is another way of determining the direction of A cross B, which is we put our hand in the direction of A and turn it towards B, and then this would be the direction of A cross B. This is the right-hand rule by which we can determine the direction of a cross product of two vectors. Now, does the order of the two vectors matter in cross product? Indeed, it does. We have to pay attention to this point. So when we say, for example, A cross B is equal to C, it's completely different from B cross A. If we switch the order of the two vectors, we will get a minus sign. A cross B equals minus B cross A. And this is a straightforward consequence of the right-hand rule for determining the direction of the cross product. Notice that if we have A cross B, we have A this way and B this way, we can determine A cross B, the direction of A cross B, using the right-hand rule this way. Set your hand along A, turn it towards B, and this up would be the direction of A cross B. Now, what if we switch the order in multiplying the two vectors? We say B cross A. What would be the direction of B cross A? That way, this would be A, and this would be B. And when we move our hand, when we set our hand in the direction of A, and we wanted to move it in towards the direction of B, then A cross B, moving from A towards B, would be pointing downward. And the pointing downward is the opposite sign as pointing upward. That means A cross B equals to minus B cross A. This is a point to remember about the cross product of two vectors, that whenever we switch the order of the two vectors when we are multiplying them with each other using the cross product, then we get a negative sign. The result is the same magnitude, but negative sign, meaning the opposite direction. Now, if we apply these rules of the cross product to multiplying the unit vectors, this is essential for analyzing vector products using component method or the analytical method. Using the definition of the cross product, we realize that the cross product of any unit vector by itself equals to 0. Thus, I cross I equals 0, and J cross J equals 0, and K cross K equals 0. And this is a consequence of the definition of the cross product, since, for example, I cross I is equal to the magnitude of I, the first one, which is 1, times the magnitude of I, the second one, which is also 1. So far we have 1 times 1, times the sine of the angle between I and I. The angle is 0, sine 0 is equal to 0. Thus, the cross product between I and itself is equal to 0. The same holds for J cross J and K cross K. The cross product between two different unit vectors is a different story. That also comes from the definition of the cross product. So I cross J, for example, equals the magnitude of I, which is 1, times the magnitude of J, which is also 1, times the sine of the angle between them. The angle between I and J is 90 degrees. Sine 90 is equal to 1. Thus, I cross J has a magnitude of 1, which is 1 times 1 times 1. What is the direction of this cross product, I cross J? The direction is determined by the right-hand rule, and it is found by applying the right-hand rule to this cross product. It's found to be in the direction of K, in the direction of Z. So I cross J equals K, magnitude 1 and direction Z, which is perpendicular to the XY plane where I and J lie. As we mentioned, J cross I, where we switch the order of the two vectors as we multiply them, is equal to the negative of I cross J. Thus, we conclude that J cross I would equal minus K, or minus J cross I equals K. These are two equivalent statements. Similarly, the cross product between the two unit vectors j and k, j cross k is equal to magnitude of j times the magnitude of k times the sine of the angle between them, which is equal to 1, and the direction of the result is in the direction perpendicular to the plane where j and k lie. This plane where j and k lie is the yz plane. The perpendicular to the yz plane is the x plane. So j cross k is in the direction of x. And following the right-hand rule, we realize that j cross k has the direction of plus I, meaning in the positive x direction. It's directed in the positive x direction. And following the properties of the cross product, we realize that k cross j, which means if we switch the order of these two unit vectors as we multiply them, gives minus sign. So k cross j would be equal to minus I, meaning it is equal to 1 in magnitude, but it is directed in the negative x direction. Similarly, the cross product between the two unit vectors k and I, k cross I, is equal to j. K and I lie in a plane which is the zx plane. The cross product of these two unit vectors would be perpendicular to this plane. Perpendicular to the zx plane is simply the y direction. The perpendicular to the xz plane is the y axis, the y direction. Thus, we conclude that k cross I would be in the direction of y, whether it is in the positive y direction or in the negative y direction. This is determined by the right-hand rule. And we find by applying the right-hand rule that k cross I is equal to j plus j, which means magnitude 1 and direction in the plus y direction. And also, using the property of the cross product, we identify that I cross j, where we switch the order of the two unit vectors, is equal to minus j, which is the same as the previous, but with a minus sign, because we just switched the order of these two vectors as we multiply them. Accordingly, when we multiply two vectors using component method or the analytical method, for example, vector A cross vector B, we write these two vectors in terms of their components. So the resultant of the cross product is called C. Vector C is equal to AX in the direction I plus AY in the direction J plus AZ in the direction K times BX in the direction I plus BY in the direction J plus BZ in the direction K. And using the multiplication of the unit vectors, the cross product between two unit vectors, and realizing that the cross product of any unit vector with itself is 0, then we get in the result the multiplication of two different components in order to make sure that the cross product between the unit vector and itself is not included. And the resultant of the cross product between these two vectors if we do the product and then add the different components, the similar components together, adding the similar components together, the components in the x direction added together, the components in the y direction added together, and the components in the z direction added together, we would get the result C equals AY BZ minus AZ BY. That is in the x direction, or I times I, unit direction I in the x direction, plus AZ BX minus AX BZ times J in the direction of Y, that's the Y component, plus AX BY minus AY BX times K in the direction of Z, that is the Z component. So this is the result of the multiplication of two vectors using the component method. And the resultant C, vector C, is a three-dimensional vector in general, having three components. These components are the x component, Cx, which is equal to AY BZ minus AZ BY, and the y component, Cy equals AZ BX minus AX BZ, and the z component, which is equal CZ equals AX BY minus AY BX. There is a good point here to remember, which is the cyclic order in which these components are arranged. Notice that if we arrange x, y, and z around a circle, then the resultant of the cross product, a given component of the cross product, follows that cyclic order. So Cx equals AY BZ, notice x, y, z, that's the sequence, minus AZ BX. The minus sign came because we switched the order of the y and z. We wrote them zy instead of yz. So that's where the minus sign comes. And similarly, Cy equals AZ BX minus AX BZ. Notice Cy equals AZ BX, the first term, that is YZX. YZX follows exactly the same sequence, the same cyclic sequence. And again, the minus sign in AX BY BZ term comes because the x and z components are switched, or directions are switched. And finally, CZ equals AX BY minus AY BX. Again, you can notice the cyclic behavior of the arrangement of these directions, where we have CZ equals AX BY, and again ZXY follow exactly the same cyclic behavior. And the minus sign in the second term, minus AY BX, comes again because we switched the order of the x and y components for A and B. And at this point, I would like to finish this lecture, and thank you for your attention.